of the particles, then the force on that particle will be along the line that joins the two particles, and if the two particles are of the same sign, it's going to be repulsive, so it's going to point away. In the other case, it's going to be attractive and it's going to point toward. All right, and that solves the problem of the magnitude and the direction. But it's really inconvenient because I need to talk too much. And so how do I solve problems talking too much? That's not good. Okay, so then that's the first thing. I want to get the right notation with Coulomb's law so that we can solve problems much easier. Okay, so then let's then consider a particle I and a particle j. I could of course call them 1 and 2, but I just call them I and j, so because later on we are going to add up, you know, the indices I and j from 1 to infinity or whatever, so let's just already call them like that. And okay, so then let me use this notation that means the force that particle I applies on particle j. Okay, so that's just notation. Okay, so in this case I would be the source and j would be the receiver of the force. Okay,
that's the force I applies to j?
Yeah. Okay, yeah, just by definition. Okay, and they are different. Ij and ji are different. Okay, they happen to be negative to each other, you know. But okay, so now I'm going to put Coulomb's law first, and I have that the force is proportional to the two charges, the product, and is also proportional to the inverse distance squared. Okay, so for now let me just write that, and then I'll fix that in a second. Okay, now first there's this, I still need to deal with this thing because it's a vector here and I don't have a vector there. I'll fix it in a second, but before I do that, normally, you know, the forces are measured in newtons. These charges, by now you know they are in coulombs, each one of them, and this is a meter. The distance is in meters, so the bottom is meter squared. So I have coulomb squared over meter squared. No way that's going to be newtons. Okay, so just by looking at the equation, I know that I need, if this is true, then I need some constant up front to fix this units. It could be 1, that constant. Okay, and not a problem. I can define that constant to be 1 if I want. But turns out that if you stick to the international system of units, meters and seconds and kilograms, etc., then you can go to the lab and measure what that constant should be to make the two things equal. Okay, so if I put 1 coulomb here and 1 coulomb here, two little objects of 1 coulomb each, and at the distance 1 meter, what force am I going to get? That's what I'm talking about. And then you measure that force, and once you measure that force, you basically are measuring that constant. Okay, so that constant k, it's more convenient, as you've seen before, not to write it like k, but to introduce a different constant. Okay, and this is weird to do that. Nobody that comes up with that equation would do that, but that's only because we want some equations later to be nicer, Maxwell's equations and some other things. Okay, so basically, since 4 and pi are known, basically this whole constant at epsilon 0. Okay, correct? That's okay. That's called the permittivity of vacuum. Okay, and also that's a strange name at this point because permittivity normally is associated with matter, but later on, now for the time being, let's leave it just as a name, but eventually we are going to introduce matter. For now, at the very beginning, we are going to study the fields in vacuum, or in air they work well. But now we want to bring in a piece of plastic, and I have an electric field in there. How does this plastic change the whole picture of what I have? Okay, so we introduce matter later, described by a property that's called permittivity. And it turns out, after you do that, that you can interpret this constant epsilon as some sort of property of the vacuum that has permittivity. Okay,
What was it called?
Permittivity.
No, with matter.
Oh, well, permittivity or dielectric constant, which are sort of...
No, that's you just said a word that started
Permittivity.
with a C. Yeah, I misread it.
Did I?
Yeah.
Constant?
Yeah, that's true.
I'll look it up in the video.
No, it's okay. Just let me know. Yeah, maybe I forgot. Yeah, I meant permittivity in any case. Yeah, well, okay. So it's 12:04. Okay, let's go for a couple more minutes. Yeah, let's wrap this up and then we'll break. Okay, so that solves the issue of units, and you can look up. This is 8, 10 to the minus 12. In the international system, you know, fine, whatever. So you can look it up. Now, this is still not a force on the right. Okay, so to do that, let's do the following. So the way we are going to think about these problems is that we are going to have particles. Okay, yeah, so let's start by talking about particles that are charged. And out of those 2 or maybe 100 particles that we have there, then we can pick one of them where we can measure the force. Okay? But all those particles are located at arbitrary locations in space. So to be able to measure something, we need a ruler, and we need to measure with respect to some origin. Okay? So basically, let's introduce a coordinate system or a frame of reference. Okay, so we have some x, y, z and some origin. Okay, so then all I need for now is to draw the origin, and let me put it here. Okay, so that's the origin, x, y, z, and the notation I want to introduce that is going to be very, very convenient is this: particle I is going to be located at vector position r sub I. That's an obvious notation. And same thing with j. Okay? So then put quotations because that's not finished, but I'm going to write the right thing now. Okay? So I'm going to write the full vector form here. Okay, so if particle I is at Ri and particle j is at Rj, how can I write the distance between particle I and j in terms of those two vectors?
Rj minus Ri.
Rj minus Ri? Yeah? So, okay, so let me draw that one. So this one up here is the vector Rj minus Ri, right? And so good. So that is still a vector. How do I get the distance out of that vector?
The distance formula?
Just the magnitude. Yeah. Just the magnitude. Okay, so if I do this, then doesn't matter which way. That's the distance, everybody agrees, but I need the square of the distance because that's the experimental statement. Okay? But if I do that, I still have a scalar. How can I make that a vector form? Okay, so I'll let you answer, but well, go ahead, I'm not going to say anything.
You say the direction of the vector
Aha, and what is the direction?
vector is r
okay. Yeah, that's a little. Yeah, that's good. The concept is perfect, but it's going to be a little bit difficult to implement. So basically, yes, yeah. So we look at the vector Rj minus Ri, and that gives us a direction. If we take, actually, if we take, yeah, no, let's do it that way. If we take a vector that is unit in that direction, that's the answer, correct? Okay, we'll check the signs and all that stuff. But hold on, the only thing we need to be careful about is the fact that I'm doing the force of I on J. Okay, not of J. So I'm interested in what is the force here. Okay? So, one moment to think about quickly. If the two charges are positive, then I get a positive product. If the two charges are negative, I get a positive product. So that means that it should be a repulsive force. So in that case, the vector should point in that direction, which coincides with the direction of Rj minus Ri. Yes? Okay, so how do I construct a unit vector out of Rj minus Ri?
The vector over that vector?
Who said that? Oh, okay, sorry, I was looking, yeah, I wasn't paying attention, thank you. Okay, so, yes, so the unit vector is the correct direction, Rj minus Ri, and then I divide by the magnitude. Okay, finally. Okay, what do we want? Okay? So, of course, we can combine those two things together, and it will give us this weird looking cube down there. But just one moment, okay? So before we get that there, let's think to see if we did everything right. So we convince ourselves that if the two charges are positive or negative, we get the correct answer pointing that way. What if one is positive and the other is negative? So in that case, this product will be negative. And so what's going to happen is that we're going to get this thing, but negative. So it's going to be attractive. That's good. So it works in all cases. That formula that we just wrote completes everything that we spend 5 minutes talking. Now we have a nice formula. We don't need to talk anymore, which is our goal. Okay? So finally then, we can state for Coulomb's law, okay, so we have that result, and that's going to be one way at least to solve some type of problems. Yes?
The last part of the equation, where is it coming from?
Because this whole thing so anytime that you have any vector, whatever, you just divide by its magnitude and you produce a unit vector.
And you added it up to get a vector.
I joined that with that. Is that your question?
Yeah, but how is it coming over there to that equation?
Here?
Yeah.
I put it by hand.
Put it by hand to make it a vector.
Exactly. Yeah. So I want, because this is unit vector, so the magnitude is already fixed, correct? And this gives me the right direction along the line that joins the two charges, either repulsive or attractive, depending on the charges. Everything works out nice. Okay?
Why you switch the I and J in parentheses?
Oh, because I made a mistake. Thank you. This is very, no, it would give me the wrong answer if I did that. Okay, good.
Also, you Coulomb island, the constant of relativity.
No, I don't. No, Coulomb only proved the square law, and I'm not so sure if he found the proportionality constant. But this way of writing things is a little bit newer than you see. Even some books will write a K here instead. Yeah. I mean, there is no reason. Let's say that let's say that you charge two small objects, and you are interested in understanding, how the force changes with distance. There is no way that you are going to be thinking about any permittivity at that stage of the game. It was impossible historically, because that came much later. Yeah, is that your question?
Yeah.
Okay. Okay. So, all right. So that's that. And all right. So let me do a couple more concepts, and then we'll have a break. So I have Coulomb's law like that. Okay. There is another very important thing that needs to be checked experimentally, which is not necessarily trivial, and which is not true in many physical systems, which is the superposition principle. Not necessarily. So what that states in this particular case is that if I have a charge J, and then I have charges 1, 2, 3, 4, 5, 6, 7, 100, okay? The effect of 1 on J, and 2 on J, and 3 on J, and 4 on J is the sum of 1 through 100 on J, that they don't affect each other. So I can add them up, okay? That's not necessarily true for all forces. There are some forces that, let's say that I have particle 1 and 2 acting on 3. So 1 on 3 gives me some answer, and 2 on 3 gives me some answer. But if I bring 1 and 2 together, the answer on 3 will be different because they influence each other. Okay? So, but in this particular case, it's not. In this particular case, the superposition principle holds, but that's something that needs to be checked experimentally, and it has. All right? So then I have this expression, and then if I'm interested in the force on J, I can write something like this, according to the superposition principle.